product rule says the derivative of f times g is the derivative of f times g plus f times the derivative of g. So to prove this, let's define the function p of x to be the product f of x times g of x. And then we'll take its derivative using the definition. P prime of x, the limit as h approaches 0, p of x plus h minus p of x over h. So, filling everything in, p of x plus h is f of x plus h, g of x plus h. P of x is f of x, g of x. And we're going to divide everything by h. All right. So now what are we going to do here? We have to somehow rewrite the top in a way where we want this f of x plus h and the f of x together without these g's in the way. And we want the g of x plus h and the g of x together without these f's in the way. Because we want to somehow manipulate this thing so that it looks like the derivative of f and the derivative of g and other stuff mixed in as well. But here the f and the g are kind of stuck to each other. I can't pull them apart. So there's a few ways that I've seen to prove this. I think this nicest way is just to use this idea that the product of two things is, you can interpret it as an area, right? So if I have the product of the numbers, say 2 and 3, well then I can interpret that as this area. So this is 2 units long and this is 3 units long, then the area in here is 6, right? You can see the 6 little squares in there. So that's the product, is this area, right? 2 times 3. So let's draw a product of f and g as an area, and let's draw the product of f plus h and g plus h. F of x plus h and g of x plus h as an area. So watch this. So imagine that f of x is some real number, and f of x, f eats that real number and spits out something else. And let's say that when I do the product, let's draw this length to represent that. So let's just draw this length to represent, let's do g first. Let's say g of x. So that distance right there is g of x. So if g of x is, so here I could say 1, 2, 3, 4, 5, 6, 7, 8. Maybe g of x is 10. And if g of x is 12, then I draw a longer line. If g of x was 3, I draw a short line, and so on. That's the idea here. Now I'll draw a line perpendicular, and I'll label it f of x. Well then whatever the numbers f of x and g of x are, 4 and whatever this was, 1, 2, 3, 4, 5, 6, 7, 8, 10, right? Then here f of x is 4, g of x is 10, and so f of x times g of x is the area of this thing right here, which is 40. And so the 4 and the 10, they're not important, but the idea is, if you take the product of f of x and g of x, that's the same as thinking about the area of the rectangle whose sides are of length f of x and g of x. Now suppose that x changes a little bit to x plus h. And maybe when x increases a little bit, let's say it increases by h, then the value of g of x increases a little bit too. So maybe g of x plus h is bigger than g of x was. Maybe it's this big. So right here we have g of x plus h. And maybe f of x, maybe f increases a little bit too. So f of x used to be 4, maybe now it increases to 6. Okay, so this distance right here will be f of x plus h. Okay. So f of x and g of x, they used to be these numbers, then x changed, it grew a little bit to x plus h. Then f of x plus h and g of x plus h, let's say they grew as well. They might grow, they might shrink. But this diagram, regardless, is going to give us an idea which is going to work, regardless of what happens. So, looking at this picture and looking at this quantity right here, this big outer rectangle represents this product right here. And this inner rectangle represents this product right here. And so if we do the difference between them, what we're getting is the difference in area between the big rectangle and the small rectangle. That's the area of that region right there. Okay, and now see, this is the trick. We can rewrite this difference, which is this area, in a different way by splitting this area up into 3 pieces. So here are my 3 pieces, okay? This piece right here, let's call this piece number 1. This piece right here, I'll call it piece number 2, and this piece right here, I'll call it piece number 3. So this f of x plus h times g of x plus h minus f of x times g of x is 1 plus 2 plus 3. Okay, it's the difference in area between the big rectangle and the small one, which is the sums of the areas of these 3 regions. So let's rewrite that limit we were doing. There's still going to be an h on the bottom, but I'm going to rewrite it so that the numerator, instead of the difference, it's going to be a sum. The difference between the big rectangle and the small rectangle's areas is going to be the sum of these 3. So what is the area of region number 1? Well, region number 1, its height, right here, is the difference between these 2, f of x plus h minus f of x. And its length this way, so it's going to be this times this. This guy right here is just g of x. So that is the area of region number 1. And similarly for region number 2, we're going to get this height right here, this time is f of x. And the width right here is g of x plus h minus g of x. That's the difference, right, between this and this. There's exactly this distance right here. So g of x plus h minus g of x. And now, all right, I ran out of room here, so I'm going to have to keep going on the next line. This is still inside this limit, right? I just didn't have room for number 3. So the third one now is what? And I might even need more room for that. Sorry about this. This third one in here is going to be, need a lot of room for it. What's it going to be? Well, its height is this right here. So this is f of x plus h minus f of x, gives you this little difference. That's the height here. And then the width here is g of x plus h minus g of x. You see this difference. So now here we've got f of x plus h minus f of x times g of x plus h minus g of x. And all this stuff is on top of h. Okay, good. So I just had to use use more than one line because I ran out of room. But the point is this numerator here, I rewrote it as the sum of these 3 areas, which is this plus this. That's area 1, area 2, and finally area 3. Okay. So now you can see the f of x plus h minus f of x next to each other. That's nice because that looks just like the derivative of f. And over here the g of x plus h minus g of x next to each other. That looks like the derivative of g. And so we're going to split this limit up into the limit of these 3 pieces. The limit of this guy over h, the limit of this guy over h, and the limit of this guy right here. Okay? So, yeah, essentially, we just have to write these fractions separately, right? Like this. This one over h, this one over h, and that one over h. We just split it up. And now we move in this limit, which we're allowed to do. Limit of this plus limit of that plus limit of that, as long as these 3 limits exist. And we'll see that they do in a sec. Okay. Here we go. So now we're up to the limit as h approaches 0 of, what was the first one? f of x plus h minus f of x times g of x over h, that was the first one, plus the limit as h approaches 0 of f of x times g of x plus h minus g of x over h, that was the second one, plus the limit as h approaches 0 of the third one. What's the third? F of x plus h minus f of x times g of x plus h minus g of x all over h. Okay, great. Now you can see here that this g of x is a common factor at the top. So I can pull it out front of the limit because it doesn't involve h. This g of x doesn't depend on h. So I can pull that factor out. So I have g of x times the limit as h approaches 0. F of x plus h minus f of x over h. Plus, same idea here. Pull the f of x out front because it does not depend on h. Limit as h approaches 0 of g of x plus h minus g of x over h. And then finally this third one, I'm going to do something slightly different. I'm going to split it up as a product of two limits. And again, I know I can do that as long as both those limits exist. The limit laws tell me that. This guy times the limit as h approaches 0 of g of x plus h minus g of x. Good. Notice that this one does not have an h, right? Because there's only one h here. It's this times this over h. So I just put the h with this one, and then I left the g of x plus h minus g of x over here. So if I just imagine those limits aren't there, right? Just make sure that algebraically, that thing, this times this, really is the same as this thing, right? All right. And now you can see we're almost done because, look at this. This is the derivative of f. So all the stuff, these limit laws that I'm applying, I'm allowed to apply them as long as these limits exist. And this one does, as long as f is differentiable at x. And because we're finding a formula for the derivative of f times g, then that formula is only going to work when you can take the derivative of f. In other words, when f is differentiable. So this makes sense. But as long as you can take the derivative of f, then yes, this limit exists and it is the derivative of f. So I'm going to write these here in the opposite order. This is f prime of x, right? So I've got f prime of x times g of x. I just wrote them in the opposite order so it looks like the product rule as I wrote it at the beginning. Now this is f of x times, what's this? This is the derivative of g, right? This is g prime of x. And again, this limit exists as long as g is differentiable at x. And so this formula is only going to work as long as f and g each have derivatives. Then, when you take the derivative of the product, you can apply the formula. Of course, if these didn't exist, then yeah, they wouldn't work. So now let's deal with, this piece right here, this piece right here. The third piece. This is the derivative of f, all right? Right here. And now the question is, what's this? The limit as h approaches 0 of g of x plus h minus g of x. Well, look at this. It's not actually an indeterminate form. This is actually, as h approaches 0, this h is going to 0. So this thing is getting closer to g of x, closer and closer to g of x minus g of x, which is just 0. So in fact, this limit is just 0. However, this limit is 0. If you think about this, what's happening is this is a point really close to x, and we're approaching x. As h is going to 0, we're approaching x here. And here we're just plugging in x. So what we're saying is that as you approach the value of x, the value of g gets closer and closer to the value you get when you would just plug in x. In other words, to say that this limit is 0 is the same as saying g is continuous at x. Is that then this value, g of x plus h, as h approaches 0, gets closer and closer to the same thing you would get by just plugging in x, which is just this guy g of x. So this limit is 0 as long as g is continuous at x. But we already up here decided, okay, for this formula to work, we want to be able to take the derivative of g. So we want g to be differentiable, and we've seen before that if g is differentiable, it has to be continuous. So this limit really is 0, as long as f and g are differentiable, as long as you can take their derivatives. Okay, but if f and g are functions whose derivatives exist, you can take the derivatives, then look what we ended up with, exactly this product rule. This goes to 0. Here, writing this in a different way, I'll just write it like this so it looks like the original way I wrote it down at the beginning. The derivative of f prime of x times g, plus f times the derivative of g. Great. So as long as you can take the derivative of f and you can take the derivative of g, then the derivative of their product is given by this formula right here.